open source distributed transactional graph database. So the agenda for this talk is, so I'm going to start by talking about the data, the complexity of data that we have today in this internet era, and how we have to battle with this data complexity every day while building applications, and how the battle can be simplified using a graph database like Dgraph. I'm going to talk about Dgraph a little more, internals of Dgraph, its architecture, and then finally see if we can do a demo depending upon the time, and then we'll have time for questions. All right, so I'm already into, so I'm going to skip this. So let's talk about data in the internet era. Data is not just growing in size, but also in its complexity and connectedness. Let's take examples to understand this more. So we'll take example of Yelp data set. Yelp is a website anyone has seen. There are lists of restaurants. Users can go there, write reviews, rate the restaurants, and see what the rating is for a particular given restaurant. So for this is a small complexity data set. We have somewhere around, say, 11 different entities. So we have query entity, which sorts queries coming from different users. Then query could be about different businesses. Business will have information about them, where they're located, what's their name, things like that. And then they can belong to a particular category. This does not work. And so on, right? So basically the idea here is that we have multiple entities, and to make sense out of this data, we have to interact. We have to interact between different entities, and then we can understand what's going on, right? So this is another example for this would be e-commerce data set. It's slightly more complex. This is the schema for the data set. This has somewhere around 20 different entities. So let's say, cannot see it, but you have customers. Customers will place orders about different products or articles. Now these products and articles will come from different merchants, and there'll be payment entity, and so on, right? So you'll see that the complexity of data is increasing, and the interaction between these different entities is also becoming more complex, right? Another, and this is a really complex data set, I couldn't even fit it on this slide. This has more than 50 different entities. So this is a GitHub data set example. So GitHub has repositories. Everyone probably would have used it. So GitHub has repositories and different users. Users could be owner to those repositories, and then it can have commits. GitHub has projects now. They recently launched GitHub Actions. So over time, the complexity of the GitHub dataset has increased a lot over time. And to keep up, and then because we have more than 50 different entities, there will be interaction between these 50 different entities. And to understand, to render a page on GitHub, we have to look at multiple entities, and then only we can present something useful and meaningful to our users. So to unearth this complex relationship in data, this could reveal a lot of interesting facts about the data, which is very meaningful and useful. This is how businesses make money today, right? So this relationship between these entities is very meaningful, and if we can make sense out of this, this is going to be very fruitful. So I'll give an example for this too. So in fraud detection, if you look at these different entities, officer, entity, or these intermediary, which is a shell company, and then address. If you look at each entity as individual, you cannot figure out what's going on, if there's a fraud going on or not. But as soon as you start looking at the relationship, you see officer can be officer of an entity, and then entity can also own another shell company. And all of them, if they have the same address, this might mean that something bad is going on, because the same address belongs to a lot of different shell companies and officers, and there might be a chance of fraud there. So as soon as we start looking at these relationships, we start to make sense out of data a lot more. And so the complexity of the data set is increasing, and then relationships are becoming more and more interesting. So that's basically the idea here. So in this, how does applications deal with such data sets when there's so much complexity and we want to understand the relationship a lot more? Okay, so we have a few sort of levers to deal with this. Let's look at SQL databases. So I'm going to take a simpler example now so that we can discuss it more. So in this case, this is e-commerce data set. We have 3 different entities. These are tables in SQL databases. So we have order table, customer table, and order status table. And so we had this data. We had different entities, and then we store this data in SQL database, and the complexity of the database remains exactly the same. We have the same number of entity that we had to start with, and in the database we have the same number of entity now. Complexity did not reduce from where we started with, so that's not very helpful. At the same time, if I want to understand the relationship between these data sets, I need to compute joins, and joins are expensive to compute. So this is not a perfect fit for these kind of use cases. On the other hand, if you look at NoSQL databases, they do give us more flexibility in terms of what we can store and how we can evolve the schema over time. But still, the join problem becomes even more difficult. Computing joins in NoSQL databases is more challenging, generally speaking. And then we still have two different entities, so the data is still not, it's still complex. We still need to look at different entities to understand what's going on, right? And then comes graph databases. So again, we started with 3 different entities, and now in graph database, we start with a customer ID, which is 201. That's somewhere in the middle, you see. And then the customer has name Aman. He lives in Bangalore, and then it can have different orders. The 2 order IDs 101, 103, and then the status of these orders could be new and shipped, depending upon the status of the order. Now we started with 1 entity or 3 different entities. Now we can look at the holistic picture right there in front of us. We understand the mental model of the data directly. There is a one-to-one mapping to that mental model to what I'm storing in the database. So I can understand and query it easily, store it easily. So this is what graph databases allow us to do. But we need a graph database that is scalable, performant, and resilient, just like SQL and NoSQL databases. If we have a graph database that does not scale, we're going to have different problems later on. And that's where Dgraph comes into picture. So Dgraph is a state-of-the-art graph database. I'm going to talk about different features of databases, of Dgraph now. So Dgraph is an open source graph database built for web scale production environments. It's entirely written in Go. It's fast and horizontally scalable. It's highly available by design. When Dgraph was designed, the first thing that we thought about is how we can make it scalable, how we can make it highly available. These are the basic things that are built in the design of Dgraph. And then Dgraph is fault tolerant. We shard data across different nodes to make sure we can scale, horizontally scale. And then computing distributed joins, filters, sorts, it's just cakewalk for Dgraph because, again, the way we store the data. We have client-side transactions, so that gives a lot of flexibility to the clients. And we'll talk about this a little more later. And then we use Raft. Raft is a consensus algorithm that allows us to pick a leader and then do state replication. That allows Dgraph to be strongly consistent, and we'll see how it is strongly consistent. So this is Dgraph. That's the URL for Dgraph if someone wants to check it out. Okay, so Dgraph is open source. We are on GitHub. We have more than 11,000 stars, and they're growing every day. We have a community of more than 2,000 developers on our Slack channel, and then we interact them over Slack. And there are a lot of issues that people come and tell us, and a lot of feedback that we get through the open source community. And then this Dgraph has been open source since the beginning, since inception. And most of the projects that we have, I actually cannot think of a repo that we have which is private. Most of the repo that we have on GitHub are public. So that would be Dgraph, and I'll talk about more projects later that potentially people can contribute to. Okay, so let's talk about the architecture of Dgraph. So as I said, Dgraph is distributed and horizontally scalable. So we'll start from the bottom. So there's a cluster of 0 nodes. These nodes, the job of 0 is to do cluster management, to make sure the cluster is stable, the data is equally distributed, and it also helps in performing client-side transactions. Alpha is where data is stored. So job of alpha is to do mutation, run queries, and things like that. And then to be able to scale Dgraph horizontally, we can increase the number of alphas. More the alphas, we can process queries faster, we can store more data, and so on. And then all of this can be accessed through Ratel. Ratel is our UI to Dgraph. We can manage our cluster through Ratel. We can also modify and query the data that is stored in Dgraph. Okay, let's talk about data sharding. And this is a really interesting problem in graph theory. How can we shard our data that allows us to efficiently query it? So what we do is we do something called vertex cut partitioning. And I'll explain what vertex cut partitioning is. So let's look at our example of This is our e-commerce example, right? So we have 201 is a customer ID, and then it has name, location, and different orders. So what we do is in vertex cut partitioning is we store data for one type of as together. So what that means is all the new as's will be stored together on one node. All the order as's will be stored together on another node or the same node. And then let's say the name edge, there's only one in this small data set, and location edge and shipped edge, all these as's will be stored together in another node, right? So we have distributed this data using all the edges. We call these edges predicates in Dgraph. So I'm going to use the word predicate, which are essentially edges, and these edges could also point to a constant value like string. So for example, 201 is the customer ID, and the name of that customer is Aman, and I'm going to use this as also as predicate. That's how we store data in Dgraph. Right? So the benefit of storing data like this is, so let's do a query on this and see how it works out. So we're going to start with customer 201, and then what I want is I want to find all the new orders that this customer has placed. So the first thing I'm going to do is I'm going to find the order edge, which is stored here, and then I'm going to find all the orders from this customer ID 201. So that, let's say the data is not stored locally. So I'll do a one network call, and I'll get all the orders for this particular customer. So now in one network call, I know that 201 customer has two orders, 101 and 103. This is one network call. So we have only done one network call, and now we have done one hop traversal in our database. Now what I want is I want to see what are the new orders that what are the new out of these 101 and 103, which orders are new orders. So I'm going to go to the node that has new edges or new predicates stored. I'm going to go there and get all the timestamps. These are timestamps when the order was new or shipped. So I'm in another network call by sending these two IDs again, 101 and 103. I'll get access to all the new orders. So in two network hops, two network calls, I can get to and I can perform the whole query. Now this might look simple to you, but think about, let's say we start with 100 different customers. I still am going to do two network calls to get this answer. All the local computation is going to be really fast. Does it make sense? So we also have something called client-side transaction. They are essentially distributed transaction. So you can, just like in Postgres, you say begin, then you do all the things that you want to do, and then at the end you say end. That becomes a transaction. So either the whole thing will be executed, or none of it will be executed. We have the same thing in Dgraph. So you can start a new transaction in your client, and then you can perform as many queries as you want. And then mutations is something, if you're trying to add new data or update some data, that's called mutation. So you can perform queries, you can do mutations, and once you're done with all of that, you can commit your transaction. And then if everything does not go according to your plan, then you can abort your transaction. And so while the transaction is going on, it's responsibility of Dgraph to give you a consistent view of the data. This property is called snapshot isolation. So Dgraph has snapshot isolation inbuilt. So you will not see inconsistent or strange things when you're trying to query data. Your view is going to be exactly fixed, and it's going to be consistent throughout the duration of the transaction. And then we use Raft consensus algorithm to ensure that if there are conflicting concurrent transactions, we abort that, we do not let the transaction come in. And then the user has to retry. This is how we are able to provide strong consistency. So Dgraph is linearizable. What that means is that there is a total order of events. So you know what sequence of transactions were done, and because you know the order of transaction, you also know what is the final state of the data, and that is going to be consistent. And then unlike eventual consistency, if you write something to the database and then read it back, you will see your data exactly what you wrote. You're not going to see some old data. So everyone sees a consistent view of the data. And let's see, I'm going to try to do a quick demo. Any Pokemon fan here? Oh, sweet. All right. I already have data loaded. I'm running 3 nodes of Dgraph. So I'm running 1 alpha here, 1 alpha here, and then 1 alpha here. So 3 alpha, 3 zeros, and Ratel. That's the standard, same architecture that we saw. All right, and I have loaded the Pokemon dataset. This is Francis Campo. So I put it together. He's a VP of Dgraph Labs. I'm just going to reuse the queries that he used. Okay, so I'm going to go to Ratel. And so let's start with finding one of our favorite Pokemon. Any favorite Pokemon? I'm just going to do Pikachu. All right, so I want name to be Pikachu. So this is GraphQL. This is GraphQL plus minus actually, which is sort of modified version of GraphQL. We are going to have compatibility for GraphQL in week or two. We are almost done. It's going to show up in our release soon. So let's look for Pikachu. But again, notice how easy the language is to use. So I'm going to find the UID and then type, and then let's do name. So I'm just saying that, hey, find a node with name Pikachu and give me this information about this data set. Okay, it does not return anything. What is that? Ah, let me see. Let's try Jigglypuff. Okay, we get some data. Jigglypuff is another Pikachu. So you see there are 3 nodes. Why would there be 3 nodes? So let's look at each one of them. So, okay. So this is our Jigglypuff Pokemon, and then you can see. Okay, this is Jigglypuff Pokemon form. So how it works is in Pokemon, and this is sort of new for me too. So Jigglypuff Pokemon has form called Jigglypuff and also called species Jigglypuff. So because all of them have name Jigglypuff, all 3 of them show up here. So let's find the relationship between these 3, what's going on here. So a way to explore this dataset is something called expand all that gives us all the edges coming out of this node. Okay, now we see something interesting. So again, we are starting with one node and we are doing traversal. So when I put these curly braces inside, nested curly braces, this does a traversal. And so it starts with a node and then traverses all the edges coming out of this node and gonna give us all the nodes around it. So if you look carefully, that's our Jigglypuff. Yeah, this is our Pokemon, and then this is the species of which is again named Jigglypuff, and these are all different properties and attributes about that species. All right, I'm going to actually expand it more, and let's see what happens. Any guesses? Okay, I'm going to move on because we have very little time. All right, so this is what happens. So now we can see we started with one Pokemon which is here, which is our again Jigglypuff Pokemon, and then we traverse all the species, and then we traverse all the Pokemon coming related to that species. So now we can see, for example, this is generation. Let me add more information here. Again, I really wanted to see how intuitive GraphQL is, and querying it does not require a lot of skills, etc. Yes, this is generation I. So these are all the Pokemons from generation I. Okay, let's do a little more interesting query. We'll do one more query, and that's it for now. We look at the gender of Pokemons. So let's just first count. So what I'm doing is I'm starting with type gender. So find all the nodes whose type is gender, and then I want their name, and then how many species of that type gender we have. So this is just a simple answer. We have 684 female, 676 male, and 10 generalist. And then the sum does not actually match because there are Pokemon which are female and also male. Okay, so let's just actually look at all of them quickly. So in this query, I'm starting with type gender, and then I'm getting the name of that particular Pokemon, and then traversing the edge species, and then I'm doing this continuously. And then this is what we get. Actually, this is not complete results. So I'm going to expand the whole thing. Hopefully, nothing goes wrong. So this is the power of a graph database, that I can directly focus on relationship and understand how my data looks like, what's going on in my data. I don't have to do any joins whatsoever. So these are the 676 male and the female and the generalist. And so the slowness actually, it is slow not because the graph is slow, but because the browser is slow. It's just there's so much data that's trying to deal with. So most likely these are all the Pokemons which are male. These are all the Pokemons which are female, and these are all the Pokemons which are male and female. Similarly, this is a different cluster we can see, and this cluster is genderless, does not related to male or female. So you can do all of this in just 5 lines of query, and that's how powerful Dgraph is. Okay, I'm going to move on. I quickly wanted to show very interesting open source projects that we have. So Badger is a fast embedded key value store. Dgraph uses Badger as its storage layer. Badger is completely open source. Dgraph is also open source. And we recently launched Ristrato. Ristrato is high performance cache. Ristrato is also open source. If you are looking for a high performance cache library for Go, you can definitely try Ristrato. And if you have issues, feel free to raise issues on GitHub and let us know how we can improve. And then that's all. Thank you so much.
So how do you ingest data here in this thing? That's the first question that I have. And second is, in social network analysis, when there are 6 degrees of separation, so have you done a study of that? And how do we ingest? So if you are a LinkedIn or if you have a local network of people connected with multiple unary, binary, or many kind of one-to-one relationships, how do you ingest data into this before you run these things?
Sure. So we have 2 ways to ingest data. One is called live loader, which is what I use to load this data into Dgraph. Live loader runs while cluster is up, and live loader is like relatively slow. Bulk loader is really fast, but you can run bulk loader before you run the cluster. You can only run it once, and bulk loader gives you like millions per RDF throughput. Dgraph is stores it in RDF format. So bulk loader is really fast, and we are optimizing it every day.
And the demo is available on your website for us.
Oh yeah, so just go to dgraph.io, and there's a lot of information out there. To answer your second question, so how Dgraph works is, to do this traversal, Dgraph uses all the nodes have integer IDs. So all these traversal is just integer operations, which are very efficient. And even sending integers over the network is also very efficient. You can compress them really well. You can compress integer 10 times to like 1/10 of their size. So traversal is really fast. But if you're dealing with large amount of data, then you're dealing with large amount of data, and there's not much Dgraph can do. If you're asking for large amount of data, it's going to return you a large amount of data. So there's not, I mean, that's the nature of the data set, and there's not much there. But the traversal are very highly optimized, and we do like one network. So let's say you're doing social network, and you have a lot of friends. All of the friends are going to be stored on single node, right? And because they're on the same node, there's no network call, or there's going to be network call to the same node. Right, so that gets optimized really well. So that's how Dgraph, and we can talk offline more.
So is Dgraph available as a service by any platform, your own platform or third-party platform?
Right, so not yet, but we are working on that, and this is one of the goal for our next quarter, that Dgraph as a service comes out. Our focus is currently on GraphQL. As soon as GraphQL is out, we are totally GraphQL compatible. The next focus is going to be on our SaaS offering.
Currently, we have to largely maintain the infrastructure to run it.
Again, talk to us. We are happy to help you with that.
Okay,
and our community is very active. We have a discourse. Our discourse is also pretty active. I go there every day to answer questions, and every engineer is there to answer questions. And because we are in both time zones, India and the US, so one of the engineers is always there. So go ahead and ask questions. All right, thank you so much.